Welcome to Digital Electronics. This is Nellie Houston. To solve parallel circuits, first we have to understand what a parallel circuit looks like. Most times we see parallel circuits drawn already in a schematic format, but that's not really what it looks like when you're building one with actual components. Let's draw a small LED. You can see the LED has a long leg and a short leg. Let's draw a second and a third. I'm going to draw a green LED with a long leg and a short leg. The short leg is the one that has the little metal inside of the LED. I'll use blue LED. So we have three LEDs that are ready to be connected. Now I'm going to draw a battery down here at the bottom. This is the positive and the negative terminal of my battery. The first thing I would like to do is show you that when you have a parallel circuit, one of the things that you may have heard is that in a parallel circuit, you have multiple pathways. That means that the electrons can travel through either the red LED or the green LED or the blue LED. And if you were to remove one, the other LEDs would remain lit and working properly. Now, this means that each LED is connected directly to the battery. So the positive side of the battery goes to the positive side of that LED, and the negative goes to the negative side of the LED, directly to the battery. So again, the red LED is connected directly to the battery. I'll use a slightly different color. Let's see, that brownish color. So the second LED is also directly connected to the battery, like so. And the last LED is also connected directly to the battery, like so. That is what it means to have circuits connected in parallel. What it means is that all devices in a parallel circuit are directly connected to the source. This means that there is only one voltage. All the devices are connected directly to the same source. Unlike series circuits where there was only one pathway, in parallel circuits there are multiple pathways. In fact, if you have strictly parallel, you're going to have as many pathways as devices that are connected in your circuit. In series circuit, there was only one pathway, therefore only one current, right? And multiple voltages because each device used a different amount of energy. Here in parallel circuits, we have multiple pathways, therefore multiple currents, and they are all directly connected to the power source, so there is only one voltage. Now, most times when you see the schematic symbol for our parallel circuits, you have again the battery schematic, which is little parallel lines, short and long, the positive and the negative side of the battery. Now, if I connect many devices directly to the battery, I could draw one right here to the right. That's one device. Again, I'm just using the resistor symbol to depict any device that uses energy instead of having to draw the schematic symbols for LED, etc. So I could draw this as being one of the LEDs. I could go this way to the left and draw the second LED. I could draw the other one this way and draw the third LED. Again, they are all connected directly to the battery. But that can get a little bit confusing. It's not pleasant to our eyes. So most books, instead of doing it like that, they draw the battery. Then they draw one device directly to the right. And then instead of starting from the battery and drawing a device directly to the right of that, they kind of say, well, it's the same place if I were to connect it anywhere along this wire. It's the same thing. It's the same connection. So what they do is they connect it at the very end of the wire instead. But it's the same connection. And the same thing down at the bottom. If this entire thing is the wire, instead of connecting it all the way at the start, they just connect it here and instead. So it looks more like a rectangle like that. And the same thing, the entire wire down here is still the same wire, and this entire connection here is still the same wire. So if I want to connect something, instead of connecting it directly to the top of the battery right there, I'm like, oh, it's the same over here, so I'm going to draw it. So most times you see the circuits drawn as I've drawn them on the right. So the entire top green connection is the positive side. So that would, on the picture, I used the wrong color. The entire green connection would be these connections right here going to the positive side of each LED. And the yellow connections would be all the connections to the negative side of the battery to each of the devices. So just to keep things simple, I'm going to erase the center part. So whenever we draw a schematic in parallel, we typically draw it in this fashion where we have more like a rectangular circuit where you have the devices just going to the right, as many devices as possible. But that's not what it looks like in real life. Like I said, if you look at the picture on the left, if you can imagine, if you had 3 LEDs or like a little 9-volt battery, that's how you would connect them. You would connect them each one directly because there's only one voltage. So I want to mention though that this voltage is the same voltage for all of them. So let's talk about what Mr. Kirchoff published. Kirchoff's laws for parallel circuit is actually the current law. So for this one, what we're going to have to do is we're going to have to look at what happens with current. But what he published was that in a parallel circuit, at each node, the net current is 0. That means that for any current going into a node, it's the sum of any currents leaving that node. So if I had to look at that node right there, that junction, the current comes in and it splits into blue and green. And if you add them, they're going to be equal to the red. So let's draw that a little bit in more detail. So here we have the current, and again, we're talking about current flow, not electron flow. The current leaves the positive side of the battery and it gets to that junction. I should clarify here, I started drawing them, but I didn't clean it up. There's no junction at that point. It's just a wire. The junctions are where I've highlighted the darker dots. There you go. So the current leaves the positive side of the battery in red, and it gets to that point where it doesn't keep going all together. Some of the current goes through the first device. Let's call this one resistance 1, 2, and 3. And some of it goes through the first device, and the rest of it goes through either 2 or 3. I used blue to show that. I'm going to use now orange. So some of the current goes through the orange from the blue. Let's pick another color, purple. And then some of it becomes purple, and it goes through the third device. So to start, the red came out and it split into green and blue, and then became orange and purple. Coming back on the negative side of my battery, the purple and the orange would come back and become blue again for this little short distance. Then the blue and the green would join again to go back to the original. So Mr. Kirchoff published that in a node, the net current is 0, meaning that in this case, the currents would add up to the total from every branch. So let's write them down. Again, for voltage total, because there's only one voltage, again, emphasize that there's only one voltage, the voltage at each device is the same, because notice they're all connected to the top on the green highlighted wire, or the bottom, the yellow highlighted wire. So I'm going to put equals, and if you have as many as you have, they're going to be exactly the same voltage because they're all connected directly to the battery. For the current, The total current, in this case, if you think of the current as the quantity of charge per second passing through a point, the amount of current leaving the battery is denoted in red, is equal to the green plus the orange plus the purple. So it's going to be the current going through the first device plus the current going through the second plus the current going through the third device, etc. Again, the blue is kind of like an intermediate uh, current because we have a wire that splits off to two more. If we were to draw it on the circuit on the left, what would happen is on the little cartoonish picture, the first LED, this one, would be the green current. Then the second one would be the orange current. And then it would be the purple current. And they would add up. Green plus orange per purple would equal to the red current coming out of the battery. So that's what he showed, that for parallel circuits, the currents add up, but there's only one voltage. Now, for the total resistance, that one's a little tricky. I would like to ask you to think of an example, an analogy to help us understand this process a little bit easier. Imagine that you go to the cafeteria and in lunch line, if you're in a lunch line in the cafeteria, and there's only one lunch line open, that's only one pathway. If they open more lunch lines options, they open more pathways, that would be like having lunch lines in parallel to each other. So that would be like some people would take the green pathway, some people would take the yellow pathway, and some people would take the purple pathway. Now, what I would like you to think about is this. What happens to the overall obstacle, to the overall resistance of getting your lunch from the point of view of like the entire cafeteria? What happens if I add more and more lunch lines, more and more pathways? If you're thinking, well, I'm going to get my lunch a little faster, there's going to be less of an obstacle, the overall resistance is going to go down, you're correct. So the more pathways we have in parallel, the more options we have for the electricity to pass through different pathways, the overall resistance in the circuit goes down. So it is inversely proportional. As the pathways go up, the overall resistance goes down. In fact, the overall resistance is always going to be less than any smallest single resistance. For example, if you have, let's say you have a pizza line only for your lunch, the overall resistance is just whatever the resistance of that pizza line is. But if we add another lunch line, let's say it's another pizza line, the overall resistance is going to be half of whatever the pizza line is, because now I have two pizza lines. Now, so as you notice, it's going to be less. It's going to be half if you have the same resistance, the same pathways. But let's say you have a pizza line, let's say the resistance is 100, and then you add another line that's like a salad line. I would think that more students would go through the pizza line, so the resistance is less on the pizza line. Let's make the salad line a resistance of 200. No matter what, the fact that you have another option, another pathway, that tells us that the resistance of the pizza is 100. If the resistance of the salad is 200, the overall resistance is going to be less than 100, because having the salad line is going to help no matter what. So the result is always that the total resistance in a circuit is less than the smallest one. The formula looks like this. It's a little scary at first, but don't fret, it's not so bad. It's the inverse, so we draw 1 over, and you have to put parentheses here, following order of operation, especially when you enter it in your calculator, because if you don't put those parentheses, order of operation doesn't work correctly. So it's the inverse of the sum of the inverses. So it's the inverse of the first resistance plus the inverse of the second, plus the inverse of the third. However many I have, I add the inverses and then close the bottom parentheses. Yeah. Another way to write that, we have to remember that if you have the inverse, especially for our calculators, when we're entering these numbers, the inverse, another way of saying 1 over x is x to the negative 1, right? So instead of putting the inverse 1 over, we can just put any number to the negative 1 exponent. And so another way to write resistance total, I'm going to write it over here to the right, is saying parentheses, you still need that parentheses to capture that grouping, is the inverse of the first resistance, so resistance 1 to the negative 1, so inverse, plus resistance 2 inverse, plus resistance 3 inverse, plus dot, 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 close parentheses, inverse of that. So the inverse of the sum of the inverses. Those are both the same way, whichever one you prefer in your calculator. Now, I have a calculator here, and that button is right there, x to the negative 1. So you can use that button. Sometimes, depending on the calculators that you have, you may have it in a different place. Or you may not have that button, in which case you could just use the original formula. Okay, so that is Kirchhoff's law for parallel circuits. Just remember, there's only one voltage. The currents add, however many branches, you add them up to get the total, and the resistances is the inverse of the sum of the inverses. Again, Kirchhoff's law is true, and Ohm's law is true for no matter what you are talking about. So Ohm's law is true for individual devices and total circuit values, but Kirchhoff's law tells us how they relate to each other. Okay, so now let's work a couple of examples. I'm going to circle Ohm's law in yellow and Kirchhoff's law in green. Okay, actually, just to not leave this one out of the way, what I'm going to do is I'm going to take this one right here, and I didn't group it properly. I'm going to lasso this entire thing. There it is, and move it down here. So you have two options, so you can work it out. Again, this is another way of saying resistance total. So you can use either Kirchhoff's laws or Ohm's law to solve these problems. I'm going to leave them over here on the side. And let's solve this simple problem, and you'll see how very doable it is. So let's say I have a battery, and my battery happens to be a voltage total of 6 volts. I do not know the current total. I'm going to leave it as a blank, and I do not know the resistance total. That's a blank. For this device, I am going to put 3 resistances in parallel. So that first device happens to be resistance 1 is 40 kilo ohms. I do not know the current through this device, and I do not know the voltage here. I'm going to connect the second device directly to the battery, but drawn to the right-hand side. And this one happens to be 30 kilo ohms. So resistance 2 is 30 kilo ohms. The current through the device is unknown, and the voltage through this second device is also unknown. I'm going to draw another device directly connected to the battery, but over here to the right-hand side. I have to scooch over a little bit. There it is. And this device is 120 kilo ohms. So resistance 3 is 120 kilo ohms. And I do not know the current through the third device, nor the voltage. Okay. Similarly to how we solved series circuits, we do the same thing. We look for to see what blanks we have to fill out and follow Ohm's law. If we can use it, we do. If not, we look at Kirchhoff's laws. If we can use it, we do use it. And you're going to go back and forth until you fill in all the blanks. So again, if I had 2 known variables either in the total, I could use Ohm's law, but I do not. So that's not an option at the moment. Same thing there. It is not an option at the moment because I only have one value. Right here, no, I only have one value. And right there, no, I only have one value. Now let's look at Kirchhoff's law, because Ohm's law at the moment is not going to give us any answers for filling in the blanks. Now let's look at Kirchhoff's law. Start from the top. Voltage total is the same everywhere. Hey, look at that. I know my total voltage is 6 volts. So I'm going to, I know that the voltage everywhere is also 6 volts. So I can fill this in that all of these values happen to be 6 volts. Look at that. We got 3 blanks already filled out. A lot of people find parallel circuits a lot faster because of this exact situation, that the voltage is the same, and you just now know that you have 2 values here, and now you can use Ohm's law to figure out the third one for each one of the devices. So let's do that. So to figure out current, it's voltage divided by resistance. So we're going to get 6 volts divided by 40 kilo ohms. That's going to be our answer. That's going to go right there. Let's work it out. So I'm going to use my calculator and I'm going to turn it on. Again, my calculator, just to keep it simple, I have it set to engineering mode. You just click over to the right, press enter, and that's going to give me all my answers in the proper notation, so I don't have to worry about a lot of translation. Again, just a little side note. If you have times 10 to the 3, that's kilo, times 10 to the negative 3, that's milli. Just a little cheat sheet on the side. All right, so let's plug this value in. 6 divided by 40 kilo. 40 second, comma, that's times 10 to the third, that's kilo. So 6 volts divided by 40 kilo ohms, that gives us 156. Oh, I didn't remind you of this one. Times 10 to the negative 6 is micro. So 150 micro. Let's put it on our little cheat sheet. Times 10 to the negative 6 is micro. So, oh, I already forgot what the number, 150, right? Yeah, 150 micro. So the answer is 150 microamps. Sometimes I have a little trouble drawing the little mu, so I just put a little u, lowercase u for micro, which is standard. All right, so we've solved that one. Let's solve for the second one here, which would be, again, to solve for current, it would be voltage by resistance. So it's going to be 6 volts divided by 30 kilo ohms, and that's going to be my answer right there. Let's plug it into our calculator, which is 6 divided by 30K, 30 second, times 10 to the third, because that's kilo, and we get 200 micro. 200 times 10 to the negative 6 is 200 micro. So let's enter our answer, 200 microamps. And lastly, again, to solve for current on the third one, I have 6 volts divided by 120 kilo ohms. Don't forget the prefixes, otherwise you get the wrong number. 6 divided by 120 to the third times 10 to the third power, that's kilo. And our answer is 50 times 10 to the negative 6, or 50 micro. So we have 50 microamps. All right, so now we did as much as we could using Ohm's law. At this point, since I've already figured out all my individual devices, I could try to solve for the totals using Ohm's law, but again, I can't because I only know one value. So Ohm's law helps me only when I have 2 knowns, which is how I solve for each of these individual currents. So now we have to use Kirchhoff's law again. So again, when we're solving for any of these circuits, it's back and forth between Kirchhoff's law and Ohm's law. So let's check out the voltages. We already know they're all the same. So with this formula already helped us, and we can't use it anymore because it's already done. For the currents, though, I want to point out that for the current formula, if we know all the currents of each individual one, which we do, we know the currents of each individual one, we could figure out the total current. So let's do that one. Let's figure out the total current. So we have to add to get the total current here. We're going to get 150 microamps plus 200 microamps plus 50 microamps. Let's plug that into our calculator. So we're going to say 150 second, comma, that's times 10 to the negative 6. That's 150 microamps plus 200 negative 6 microamps plus 50 negative 6 microamps. So that's a total of 400. Maybe you didn't need a calculator for this because maybe you could figure out that 150 plus 50 is 200 plus 200 is 400. But just to make sure you follow how to enter the numbers in the calculator. So my answer for the total current is 400 microamps. So let's type that in as, or write it in as our answer, 400 microamps. Lastly, now we can use Ohm's law, or we could use Kirchoff's resistance formula. So either way, I'm going to show you how to do, I guess, like I said, let me just clarify that. I could use Ohm's law to figure out the third value right here, dividing voltage by current. Or I could also use Kirchhoff's law, my resistance formula, to add all the different resistance inverses to get the total resistance. You know what? I'm going to show you both ways, one to solve it and the second to verify it. Okay, so let's start with Ohm's law by getting the resistance is voltage divided by current, so it's going to be 6 volts divided by 400 microamps. Let's plug it in to make sure we get a value that makes sense. 6 divided by 400 times 10 to the negative 6. So that is 400 microamps, and we get a total of 15 times 10 to the 3, which is 15 kilo. So 15 kilo ohms. Let's see. First of all, let's see. Does it make sense? When we check them, our resistance is 40 kilo, 30 kilo, and 120 kilo. So remember what I said about parallel circuits in parallel, that the overall resistance is always less than the smallest one. So the smallest one in this case is 30, and total is 15. So it's kind of making sense, but let's double check it. So let's check, since we used Ohm's law to figure out the 15 kilo ohms, let's use Kirchhoff's law. So again, there's two ways to plug it in. It would be 1 divided by 1 over 40 kilo ohms plus 1 over 30 kilo ohms plus 1 over 120 kilo ohms. Or the way I like to type it in the calculator, because it's a little bit faster, is 40 kilo ohms inverse plus 30 kilo ohms inverse plus 120 kilo ohms inverse, the inverse of that. Either way is correct. Let me show you how I would type it in both ways. So to do it the side on the left, I would do 1 divided by, open parentheses, 1 divided by 40 to the third plus 1 divided by 30 times 10 to the third plus 1 divided by 120 times 10 to the third, close the parentheses. Don't forget to close the parentheses, and you get 15 kilo. There was a lot of 1 divided that there was typing, so like I said, I prefer to do it like on the right hand side. So you type parentheses and you say 40 kilo, and then you press the inverse key, plus 30 kilo, and then you press the inverse key, plus 120 kilo, and then you press the inverse key, and you close the parentheses and press the inverse key one more time, and you get the same answer. So I guess it's just whichever way you prefer to type it into your calculator. The best way is the way that works for you, of course. But again, we measured and we calculated it, and we saw that the values are the same. So you can see how to solve for these problems is very similar to the process for series circuits, just using the parallel formulas. Let's try one last one just to make sure you are following along. What I'm going to do is I'm going to take this example in the center and move it out of the way so that I can still keep referring to my formulas right here in the center. Here we're going to have another example right there. So let's copy this example down. So I'm going to have battery. This time I do not know the total voltage. I do not know the total resistance, but I do know the total current is 40 milliamps. Now I'm going to have 3 devices as well. So we have 1 device, 2 devices, and 3 devices. Okay. Now, for the first device, I know that a current is 10 milliamps. The second one, I know the current is 5 milliamps. And the third one, I know the current is, oh, I'm not giving that one. That's an unknown. What I am giving is the resistance of the third device is 8 kilo ohms. This is a little tricky. So what's missing? So I'm missing the voltage of the third device. I'm missing the voltage of the second, the voltage of the first, and I'm also missing the resistances of these 2 devices. So we have some blanks, but they're slightly different. They're not quite the same as the first example. Okay, so let's see what we know and what we don't know. Let's see, the first thing to check is, for me, it's faster to use Ohm's law. Do I have any 2 values that I can plug in that I can figure out the third one? The answer is nope. Ohm's law at this moment doesn't help us. Do I know Kirchoff's voltage law tells me that they're all the same? Do I know any voltages? Nope. At this moment, voltage law from Kirchoff is not going to help me. What about the currents? Can I add them up? Wait. Oh, yes. What kind of? For current, they all equal to the total. So I have 40 total, 10, 5, and I have a missing one. So there you go. I can kind of add them and subtract from 40 and figure out the missing piece. So do you see how this one is a little bit different? So what we're going to do for this one is we're going to use Kirchhoff's current law, knowing that they have to add up to 40 milli. I need to know what the blank one on the third place is. Okay, so here we go. Let's work on that one. So let's fill it in. So I know that 40 is going to be 40 milliamps. Sorry. So we're going to say 40 milliamps is equal to 10 milliamps plus 5 milliamps plus X milliamps. Well, I think it's easy for you to realize that it's just going to be 40 milliamps minus 10 milliamps minus 5 milliamps. And that's going to be equal to our unknown milliamps. That's going to go right there. So 40 minus 10 is 30, minus 5 is 25. Let's just double check, making sure we don't mess up on simple math. 40 milli, I don't have to, since they're all milli, I'm just going to leave the units out. 40 minus 10 minus 5, that gives us 25. Very good. So yeah, 25 milliamps is the answer. Oh, I can't type correctly. 25 milliamps is the answer left for the unknown. Now we have all the currents. And check it out. Now that we've solved for that one using Kirchhoff's law, I can use Ohm's law to solve for the third one. The third value I'm missing. So voltage is current times resistance. So to figure out the voltage here, it's going to be 25 milliamps times 8 kilo ohms. So let's plug that one in. So 25 milliamps, so 25 times 10 to the negative 3 times 8 kilo ohms. 8 times 10 to the positive 3. And our answer is 200 without a prefix because it's times 10 to the 0. So it's just 200 volts. So let's plug those in. 200 volts. Very well. Hey, I have voltage for one of them. And remember what's going on? There's only one voltage. So if you recall, the voltage, if I know one of them, it's going to be the same everywhere. So that's actually pretty cool because I know that if the voltage is 200 for the third device, I know it's 200 for the second device, for the first, and that's the voltage of my battery. So I filled in a lot of blanks already. All right, so now the one thing that's left is the resistance of each one and the resistance total. So let's use Ohm's law to solve for those. Ohm's law to solve for that one, and that one. And then we can verify to make sure that we did it right with Kirchoff's law. So the resistance is going to be voltage divided by current. So it's going to be 200 volts divided by 5 milliamps for that one. So it's going to be 200 divided by 5 times 10 to the negative 3, because 5 milliamps. And that's 40 kilo. 40 times 10 to the 3. So 40 kilo ohms. Nice. Next, we're going to solve for the second one, which again is 200 volts divided by 10 milliamps. Let's plug it in, which is 200 divided by 10 milli. And we get 20 kilo. So this one is 20 kilo ohms. And the last one, to figure out the resistance is, so this one's going to go in here, is going to be 200 volts divided by 40 milliamps. Let's plug that in our calculator. 200 divided by 40 milliamps. And we get 5. That's a smaller number. 5. Wait, 5 what? Did it have a prefix? Yeah, 5 to the third, 5 kilo. 5 kilo ohms. Okay, so it does make sense in that, remember, the overall resistance of my device is smaller than the smallest individual resistance. The smallest in this case is 8K, so the total is slightly less than that one. But let's verify that we did it right by plugging it into our formula. So it's going to be the inverse of 1 over 20K plus 1 over 40K plus 1 over 8K. Or you can type it the other way in the calculator. I'm going to write it like that, and then I'm going to type it the shorthand way. So it's going to be 20 kilo inverse plus 40 kilo inverse plus 8 kilo inverse, close parentheses, the inverse of that. And indeed, we get 5 kilo ohms. So we have verified that that is 5 kilo ohms, and it does match our final answer right there. So there you have it, folks. These are two examples of how to use the formulas from Kirchoff's laws to solve for problems. The key things to remember is that there's only one voltage, meaning that each device is directly connected to the battery. And you always check with Ohm's law if you finish with Kirchoff's or the other way around. I just wanted to show one last little tip and trick. I want to tell you this. Because the formula is just a ratio, I'm talking about the resistance formula, that one right there, the resistance formula. It happens to be that if you have two devices in parallel that are identical, I mean, I'm not even going to put a battery, I'm just going to leave it like that. And let's say I put an ohm meter here, and I measured from there to there. And I had, let's say, 50 ohms here and 50 ohms here. If I plug it in, 1 over 50 plus 1 over 50 happens to be half, which would be 25 ohms. If I do the same thing, if I have another device, let's say it's 200 ohms in parallel with another 200 ohms, again, you plug it in 1 over 200 plus 1 over 200. It happens to be half, which would be 100. And it continues. So whenever you have two resistances that are identical in parallel, it's just going to be half. Also, if you have 3 or 4 or 5 or however many, if they are the same, let's say now we have 4, 5, however many you have. And let's say each one is 200, 200, and 200, and 200. Well, it works out that it's just the resistance divided by however many there are. So in this case, there's 1, 2, 3, 4. So there's going to be 200 divided by 4. And I believe that is 50, right? So the total is going to be 50 ohms. So in short, if you have identical resistances in parallel, the total resistance is the value divided by the number of pathways. So if you have 10 resistances in parallel and the resistance is 100, for each one, it's going to be 100 divided by 10. If you have each resistance is 1,000 and you have 10 of them, it's going to be 1,000 divided by 10. If you have 3 resistances and each one is 100, it's going to be 100 divided by 3. Whichever way, it makes it pretty easy to solve. If you have exact resistances, that's a cool trick to know. All right, that's it for now. I hope that was helpful to you, Kirchhoff's law. Thank you.